So Kevin, Nishant and I are not co-hosts. I don't know if it's required to.
Yeah, I think it's better to promote them to co-hosts. Tancred and Nishant, yeah. Huh, okay. Thanks, Leo, for the answer. Okay, very good. And then, yeah, Nishant Chandran also should be promoted to co-host.
We are now recording and broadcasting. You can start.
All right. Welcome to the next session. We are very happy to have Dima Kogan giving the talk. This is a joint work with Henry Corrigan Gibbs on private information retrieval with sublinear online time. This is the winner of the Best Young Researcher Paper Award. And Dima and Henry have made a hat trick, I think, of Best Young Researcher Paper Awards from Eurocrypt in 2018, TCC in 2019, and now Eurocrypt 2020. So look forward to hearing the talk.
It's the same paper all the time.
Thank you very much. I'll be playing a pre-recorded talk, so just a second.
Hi, I'm Dima, a fourth-year PhD student at Stanford, working with Dan Bonnet, and today I will be talking about private information retrieval with sublinear online time. This is joint work with Henry Corrigan Gibbs. Thank you for watching this virtual presentation, and I hope you enjoy it. In this work, we present a new method for making PIR faster. Specifically, our new PIR schemes push the bulk of the work to a preliminary offline phase, during which the client fetches a short string from the server. In a subsequent online phase, the client can privately query the database, and the server can respond to the query very quickly, in time sublinear in the database size. Moreover, our schemes do not require any additional storage on the servers. First, let me give you a little bit of background about PIR. Private information retrieval, introduced by Shor, Goldrach, Kushilevitz, and Sudan, is a cryptographic protocol between a database and a client that allows the client to read any record in the database without the database server learning which record the client is reading. And throughout this talk, we will model our database as an n-bit array, meaning each record is only a single bit. However, using standard techniques, PIR can be applied to databases with larger records, as well as to key-value databases rather than plain arrays. PIR is useful in scenarios where the user's query contains some sensitive information. For instance, a query to a database of medical conditions might reveal some information about the user's disease, and a query to a database of stock prices may contain information about the user's financial interests. And in both cases, the user would ideally want to keep his query private. PIR is also useful as a building block in larger privacy-preserving systems for applications such as private messaging, search, or DNS. More formally, a PIR protocol has to satisfy the following properties. First, correctness, meaning that an honest client interacting with an honest server should learn the correct value of its bit of interest. And second, security, meaning that the server should learn nothing about which bit the client is reading. And as always, learns nothing means that the view of the server when the client is reading bit I should be indistinguishable from the view of the server when the client is reading bit J. And actually, there's a trivial protocol that meets both of these requirements. The client can simply download the entire database and perform its query locally. However, downloading the entire database is impractical in most settings. So we would want the protocol to be efficient, meaning that the total communication between the server and the client should be minimized. And indeed, these requirements can be met. The same work that introduced PIR also presented a protocol that achieves sublinear communication by replicating the database on 2 or more non-colluding servers. And ever since, there has been a long line of work improving the communication complexity of multi-server PIR, and today, the best PIR protocols have communication complexity n to the little o of 1, and they provide information theoretic security. Moreover, if we settle on computational security, recent protocols achieve logarithmic communication just from one-way functions. In addition, soon after the original multi-server PIR paper, Kushilevitz and Ostrovsky showed that one can build PIR with only a single server, but here computational assumptions are necessary. Today, we know how to build PIR with polylogarithmic communication complexity in the single server setting from a wide range of public key assumptions. So it seems that in terms of communication, our situation is actually very good. However, the situation is not as good if we look at computation. In fact, in the protocols on the last slide, a server needs to scan the entire database to respond to a query. And in practice, doing linear work on every query is very expensive. It turns out this is in some sense inherent, since the expected server work in any PIR protocol must be linear in the database size. The intuition is that a server must touch every bit of the database, since if it doesn't touch one of the bits while it is responding to a query, it can guess that this untouched bit is not the bit the client is attempting to read. And although it is not at all trivial, it also holds in the multi-server setting. There have been several approaches to reduce the server work in PIR by somehow circumventing this lower bound. A very promising approach is called PIR with preprocessing, where the basic idea is that the servers store the database in encoded form, and using this encoding, they can respond to user queries much faster than in linear time. The catch is that now this encoding of the database, which the servers need to store, is much larger than the original database. So for instance, to get query time n to the 0.6 using this approach, the servers need to store code words that have length larger than n cubed. And this is not very practical for databases that are gigabytes in size. There have also been other approaches that reduce the server's work in PIR by batching queries, sharding the database, relaxing the privacy guarantees, or moving the more expensive part of the work to an offline phase. However, the overall amount of online work in all of these approaches is still linear in the database size. So the plan for the rest of this talk is, first I will define the offline-online model, then I will present our results in more detail, then in the main technical part, I will explain the main ideas behind our two-server PIR construction. In the end, I will talk a little bit about the single server setting, and then I will conclude. But let's start by defining the model. For simplicity, we will be working in the two-server setting, and we will refer to our two servers as the left server and the right server. And crucially, we assume that the two servers are non-colluding, meaning that the adversary controls at most one of the two servers. Our scheme starts with an offline phase. In the offline phase, the client interacts with the left server, who provides it with a hint, which is a string that depends on the database itself. The length of the hint has to be sublinear in the database size, as otherwise the hint could just be the entire database. And to give you a preview, in our constructions, the hint will be about square root n bits in length. To produce this hint, the server does need to perform a linear amount of work, but the key point is that this phase can take place before the client has decided on which bit it wants to read from the database. So the server has much more flexibility to perhaps run this phase overnight and without any strict latency requirements. So after completing the offline phase, the client stores this hint and waits for the online phase to begin. And note that unlike in the PIR with preprocessing approach, the servers don't use any extra storage, and in fact, they just store the database in its original form. And then the second phase is the online phase. Here, the client decides on the actual input index I, the index of the element from the database it wants to read, and it uses the locally stored hint to generate the query to the other server, the right server. And the response to this query, together with the hint, allowed the client to recover the bit of interest x sub I. And crucially, the server's work in this phase, as well as the communication between the client and the server, has to be sublinear in the database size. I should mention that an offline-online model has been considered in the past, yet previous schemes in this model either have linear online time or require additional storage on the server. So now we can state our results in a bit more detail. Our first result is a two-server offline-online PIR scheme with square root communication and square root online time. And for simplicity, throughout this talk, I will avoid explicitly writing factors that are polynomial in the security parameter lambda and polylogarithmic in the database size n. So when we talk about square root of n, what we really mean is O tilde of square root of n times some polynomial in lambda. And this construction uses only basic symmetric key primitives, so it is concretely efficient. The construction also has the extra property of allowing to execute multiple online queries without having to redo the offline phase from scratch each time. And this means that the linear cost of the offline phase can be further amortized across multiple queries. Our second result is a single server offline-online PIR scheme, which uses n to the 2/3 communication and n to the 2/3 online time. In terms of assumptions, what we need here is black box use of any single server PIR scheme with low communication and additively homomorphic encryption. And both of these can be built from a variety of public key assumptions. If we are willing to use heavier tools, namely FHE, then we can recover back the square root of n running time. And an extra property of our single server scheme is that it doesn't require any public key operations in the online phase, which makes the online phase even faster. A drawback that our single server scheme has is that unlike the two-server scheme, it requires a separate execution of an offline phase before each query. And finally, we give a lower bound for offline-online PIR schemes in this model, where the servers need to store the database in its original form. Specifically, we show that the product of the communication C and the online time T must be at least linear in the database size. And this matches our two-server scheme and the FHE-based single-server scheme. And I should say that this lower bound holds even in the computational setting. So now we proceed to the main technical part of the talk, and we'll see how that two-server scheme works. So let's start with the offline phase. Here the client chooses m random subsets for a parameter m that we will set later. So these are m subsets where each subset contains square root n independent random elements from the universe of 1 through n. And then what the client does, it sends those sets to the left server. And naively sending this amount of information would take too much communication, so we could either generate those sets using some shared randomness between the left server and the right server, or we can just use a pseudorandom generator, and then the client only needs to send a seed to the left server. So when the server receives these m sets, for each of these sets, it computes the parity of the database bits that are indexed by the set. So overall, it computes m such parity bits, one for each set, and sends them back to the client. And what the client does, it stores the collection of this set and their parities as the hint. So the hint contains a collection of sets and their parity bits. And that's the entire offline phase. Notice that there's no index I in the picture, so everything here is completely independent of any particular database index, and this can happen offline. Now we move on to the online phase. Here, the client decides which index I it wants to read from the database. And the first thing it does is to look for a set in its local collection that contains the index of interest I. If none of the sets contain index I, then the client fails, and we will later see how to deal with all these failures. If such a good set Sj does exist, then the basic idea is that the client removes element I from the set and sends the set S prime, which we call the punctured set, to the right server. Except that with some small probability of roughly 1 over square root of n, the client actually does something different. It sends to the right server a random set S prime that does contain index I, and this is also considered a failure, which we will account for later. In any event, the write server receives from the client the set S prime, which has size square root n minus 1. And just like the left server did before, it computes the parity of the database bits indexed by this set and sends back the parity bit back to the client. And now the client has two bits. It has the parity bit hj from the hint, and it has the answer bit a from the write server. So the client just outputs their sum mod 2. And note that hj is the sum of all the database bits in the set sj, and the bit a is the parity of all those same bits except bit xi, since the client removed index I from the set sj. Therefore, the sum of those two bits is exactly the bit of interest xi. And that's the construction. Okay, so now let's go back and look at those two failure events. So the first failure event is when the collection of sets doesn't cover all indices. And here is where we choose the number of sets, little m, to be roughly square root n times log n, and then by a standard coupon collector argument, the failure probability of this first event would be something negligible in n. And then the second failure probability, it comes directly from our construction, which is the event that we send this random set S prime that contains I and consider this a failure. And this happens with probability roughly 1 over square root of n, which is also the overall failure probability. So what we do next is we actually want to drive down the failure probability even further. We want it to be negligible in the security parameter lambda. So we repeat our entire construction lambda times in parallel. And this is not the most tight analysis. But in any event, now that we have lambda instances, the probability that all those instances fail happens with a probability that is negligible in the security parameter lambda. And one point that I want to emphasize is that those repetitions, they include both the offline phase and the online phase. So in fact, the client generates lambda independent hints in the offline phase. And it repeats this online phase lambda times in parallel, completely obliviously of any successes or failures it has in some of those iterations to avoid leaking anything from those failures to the server. Okay, so that's overall we end up with a negligible failure probability, and this is the correctness that we want. Okay, so now we turn to doing the sketch of the security proof. So first of all, the security from the left server is actually pretty immediate. The sets that the client sends to the left server, they do not depend on the index I in any way, so they can't possibly leak anything about index I. The security against the right server is trickier, since the set Sj clearly depends on index I. And here is where the non-collusion assumption and this weird-looking sampling come into play, since they guarantee that the resulting set S prime is a uniformly random subset of size square root n minus 1, independent of I, and therefore hides I from the right server. And to see this, we can identify the distribution of the set S prime with the following way to sample a uniformly random set. So fix any index I, and then a uniformly random set of size square root n minus 1 should contain this fixed I with probability square root n minus 1 over n, which corresponds to the first case above. And with the remaining probability, the set should contain elements which are all distinct from I. And this is what happens in the second case, where we explicitly remove I from the set Sj. So overall, the set S prime is independent of I, which shows security from the right server. And just one more thing, if we generate all the sets using a PRG rather than using true randomness, then we simply lose some negligible distinguishing advantage, but the argument is basically the same. Let's now look at the efficiency of our protocol. The communication in the offline phase consists of the client sending square root n random sets, which we assume we can shrink using either a PRG or shared randomness. And the server sends back square root n parity bits, so the total communication in the offline phase is square root of n. In the online phase, the client just needs to send a single punctured set to the right server and get back one parity bit, so the total communication is also square root of n. In terms of computation, the offline phase is linear, since the server needs to process all the sets, and the online phase runs in time square root of n, since the server just needs to process a single set. Next, I want to discuss a main feature of our two-server scheme, which is that it amortizes the linear cost of the offline phase by running multiple successive online queries without having to redo the offline phase each time. The problem in naively running multiple queries as is that the client must be careful not to reuse the same set Sj for two different reads. If the client would accidentally do that, then from the symmetric difference between the two appearances of the same set, the server would be able to learn the client's indices. So instead, the idea is that we refresh the hint by sampling a replacement set S-new, and then fetch the parity of this new set from the left server. And we need to be careful to sample the new set in a way that preserves the joint distribution of the sets in the collection to provide correctness guarantees for future queries. And also, everything needs to be done in a way that hides index I from the left server. This refreshing procedure can be done any polynomial number of times, and the bottom line is that now preparing for the next query only takes square root n time rather than linear time, which is what redoing the offline phase from scratch each time would have cost us. So to sum up the two server results, we show the scheme with square root n communication, online time, and even amortized total time per query. The client storage and running time in our scheme is square root n, and the scheme requires either pseudorandom generators or shared randomness between the client and the left server. We also have extensions to our scheme, such as trading off communication for online time and vice versa, and there's also a statistical security variant that works even when there's no shared randomness. Finally, using punctuable pseudorandom functions, we can have the client send only a short description of a punctured set, which shrinks the communication in the online phase to only log n. The resulting scheme is highly efficient in terms of communication, though the client's running time is not as good as before. The last thing I want to talk about before I conclude is to give you an idea of how our single server scheme works. The general idea is that we want to transform our two-server offline-online scheme into a single-server scheme by running both phases on the same server. However, this breaks security, which crucially relies on no single server seeing both the offline and online queries. To work around this, the client encrypts the offline query using homomorphic encryption, and the server evaluates the offline phase without seeing the client's query in the clear. The online phase remains the same as before. And here we have two options. We could either use fully homomorphic encryption, which preserves the asymptotic running time of square root of n, or we can use an additively homomorphic encryption scheme, but then having to express the scheme as a linear transformation forces us to use a less efficient representation of the sets, which results in a worse asymptotic running time of n to the 2/3. The advantage is that the second scheme is concretely more efficient. So to summarize, we have seen a new type of PIR schemes that get sublinear online time and require no additional storage on the server. In the paper, we also have a lower bound for this model, which we prove using a reduction from a classic problem by Yao. And finally, I want to mention two open problems. First, it would be great to get schemes with better running time on the client's end. In our scheme with log n online communication, the client's running time is n to the 5/6. It would be great to make the client more efficient. And second, one limitation of the offline-online model is that the offline phase is separate for each client. It would be very interesting to be able to somehow amortize the offline cost across multiple mutual distrusting clients. And with this, I'll conclude.
So thank you very much, Dima. So we're not going to go to the questions, so I'm going to look at the Q&A. So currently we have two questions, so if you have questions, please add them to the Q&A. So the first one is by Kevin McCurley. The age-old question in many theoretical aspects of cryptology is how practical they are. Do you know how much progress has been made in making these techniques practical? Are there possibilities to weaken the security model in exchange for better practicality? Or should we think of these techniques as being only useful for small databases?
So I think there's definitely been progress in trying in actually deploying PIR schemes, and even in systems conference, there's been a few works in the past few years to try to basically deploy or build systems that run PIR and even in the single server setting based on I think mostly lattice-based crypto. And it's also, I guess it's also a goal of our work to try and make these things even more practical. So I think roughly speaking, with all those approaches that require linear work, in many cases, the bottleneck could be even just linearly scanning the memory. And so you could imagine that roughly you could now, like the memory bandwidth would be like, say, tens of gigabytes per second. So it allows you, say, it allows you to maybe, if you have a database a few gigabytes in size, to get with linear time, something like a few queries per second. And hopefully with our work, we're actually looking into implementing this. If we can get down to square root n memory bandwidth complexity, then we hope to get like at least a few dozens or maybe even over 100 of queries per second from a single machine.
Thank you. So second question by Antigone, Polychromy. What is the multiplicative depth of FHE in the one server solution?
So first of all, I should say we haven't tried optimizing it too much, but it seems to me that I believe we could maybe hope for a polylogarithmic depth because we would need to send out, as I said, we need to send out a description of a square root n set and then take a XOR of elements from the database. So I believe lookups could be done in logarithmic and then summing things up as well. So I'll probably should look into it more carefully, but I believe there's hope to get like polylogarithmic or maybe even logarithmic.
Next question by Baptiste Lambin. Might be a naive question, but could adding more server improve the scheme in any way?
Yeah, that's a good question. We thought about it not too much. It seems that somehow our approach is tailored at the two servers. Yeah, I think it's an interesting direction. Yeah, it would definitely be very interesting if we could improve something.
Thank you. Next question was in the chat by Mariana. If the offline phase is different per client, what is the comparison with ORAM, which provides sublinear computation?
So yeah, definitely the fact that we have to run the offline phase for each client definitely adds cost. I think the main difference would be that with ORAM, you basically have to transform the entire database. It basically creates something like at least a linear size or a linear size encoding on the server side. So that would mean if a bunch of clients want to use an ORAM solution instead of say our approach, then the server will need to store multiple different copies because the secrets need to be different for each client. And somehow, at least for us, the motivation was like the servers usually don't want their systems to scale, like definitely in terms of storage with the number of users. So if each client can contribute a little bit storage on the client side, this could be preferable and might incentivize more servers to deploy it. So I think that would be the main approach. Basically, the storage cost on the server in our scheme does not grow with the number of clients, and in a normal solution, it will.
Thank you. So there's a follow-up about the previous question about fully homomorphic encryption. If you use fully homomorphic encryption for lookup, don't you need linear complexity?
So the circuit size would definitely be linear. I'm just trying to I'm trying to think whether you could do it with a lower depth. Yeah, I should probably look into it a little bit more offline. I don't want to make a mistake now. Maybe yeah. It's I guess yeah. I think the lookup will be the critical path, so whatever that would take.
Thank you. So next question by Ao Chen. Is there any result regarding to the variant where client cannot learn more than the item it requires?
So that yeah, basically in kind of in a symmetric peer setting, I guess that would be where there's privacy requirements both sides, if I understand correctly. So we did actually this is a problem we haven't looked at. And obviously, as I think in this approach where you have some kind of pre-computation, I think it's bound to leak something about the database to the client, because it's kind of it's performed independent of the particular index you're reading, and unless, I don't know, maybe there's some way to encrypt it or something like that. But I don't see at least how this can be done easily. Yeah, so maybe that's again, that's an interesting direction to look into more.
Yeah, Evgeny has a question. Did you look at the trade-off where server can store a little bit more than n, like maybe n squared? Seems like some parities can be computed slightly faster, but maybe more.
So yeah, I think this, in some sense, kind of pre-computing some of the parities. This is more of the approach taken by the peer with pre-processing. So maybe there's a way to combine it. Somehow we would, I think, even we're aiming at avoiding even something like a quadratic blow up. So maybe, I don't know, maybe linear would be the kind of the line of division here. So yeah, I think maybe some additional factors can be saved.
Evgeny has a follow-up. Will your lower bound also extend?
Okay, that's so yeah, the lower bound is actually limited in the sense that so no, the lower bound, I would say the lower bound does not capture improvements that can happen from suggestions as the one that Evgeny makes of basically either increasing the size of whatever the server stores, or even just modifying and not storing the original n-bit database, but somehow encoding it even in a linear size encoding. Our lower bound does not hold. So that's, I think, I think in general that there is, even if we go back at the peer with pre-processing approach, there's quite a gap there between the upper bounds and the lower bounds. So there's hope, even something that's better in our scheme and better than the current concretely schemes we have with peer with pre-processing. The ideal scheme would be if we can do some linear size encoding on two servers, say, and then respond faster than square root, even polylogarithmic. With our lower bounds do not. These are the lower bounds from the old work from peer with pre-processing. They're not strong enough currently. So there's hope there for progress with all these approaches. Even, yeah, as I said, even if you just allow for linear blow up, which would seem to be practical if one can do that.
So I have a follow-up question also. So right now, the peer is described in terms of a database of bits. If we're storing, strings, in concrete application, you're going to store some longer elements. Can your method be applied directly where the ints are longer than just bits, or do we need to transmit the queries bit by bit?
So it seems that I guess the standard way to do it, which I think would be the way here, is that you'll basically send one query, you'll upload one query, and then the server respond basically with respect to each bit in the block. So if you have blocks that are equal size, which is also quite an assumption in many cases, then I guess you would just get a multiplicative cost of the record size on the download. Then there's maybe more you could try to do slightly something more clever, which is instead of looking at it as kind of independent blocks, as block of independent bits, you could try and rebalance the parameters of our scheme. Once the blocks get large enough, basically you can, in our scheme, we can tune the running time and the communication, and so I think once your blocks become kind of comparable, say to square root over n or something, it might be worth to look back at which we kind of square root n communication, square root n time is kind of the simple rebalancing that we chose, and you could maybe revisit this again once the blocks get big enough, because only the download communication gets multiplied. Yeah, and then if the records are also, the second thing would be if the records are not the same size. So say you have, I don't know, you have Netflix videos or something like that, which is one application people in the past have been looking at for PIR. Then the standard thing would either do some kind of padding to say maximal size, or maybe or do. Or if you start chunking your records into blocks, then you need to be careful that the number of blocks you fetch isn't leaked. So I would guess you would have to do some of these approaches. But yeah, these are kind of more classic tools. It's not something that we've developed specifically for our scheme.
Thank you. So if anyone else has a question, a question just came. So the bound says that CT is not equal to N necessarily. With the single server solution, both C and T are of the order of N to the 2/3. Why was it not possible to reach N to the 1/3 for one of them?
Yeah, so I guess it comes down to the question of why is the scheme that we get from linearly homomorphic encryption is not as good as the one that we get from FHE, because the one that from FHE does match the bound, and the linear homomorphic encryption scheme is more limited. And the reason is that basically, if we're using a more restricted homomorphic scheme, that we need to express our computation as say a linear function. And this basically means that the query cannot be represented as succinctly as it does when you have no restrictions on the computation. So for example, if I can just send you a description of a set with the list of elements, then it's like you can represent a set of size square root 10 using roughly square root 10 log n bits. But now when you have the computation needs to be kind of linear in your description, then you need to have a more redundant description of your set. So say an n bit vector with indicators of which are the elements of your set. So basically, because the representation of the queries blows up, we need to kind of rebalance all the parameters. And now the communication grows. Yeah, so that's, I hope it's kind of gives some intuition, and yeah, the paper has more details.
We have two more questions. Paul Grubbs asks, how easy is it to find practical settings where non-colluding servers could run a two-server PIR protocol? Is a non-collusion assumption realistic?
Yeah, that's a very good question. I guess it seems it's. I think it depends on your threat model. So I think that nowadays you probably have you could find either, I don't know, commercial organizations or political entities that you trust to be sufficiently competing, maybe that you could at least for some applications it might be reasonable to put trust in that. I don't know, you could choose Yandex and Google or your yeah, I guess I think that's I definitely, so personally, I mean, it's kind of subjective. I personally feel that there are definitely applications for which such assumptions could be reasonable. In some sense, I feel like more than this, the problem, maybe the issue is not only security, but also kind of the complexity in deployment that it creates. Because if these organizations are now competing, they somehow, you need to coordinate to make things work. So, but I believe these are problems that can be automated and solved, hopefully.
And Nathan asks, would the result extend to a database as a vector over FQ? It seems that the XOR operations could potentially be replaced with addition mod Q.
Yes, so I think that. Yeah, that's yeah. I think that in some sense, this is basically this is and I think this would work, and this would be another view of larger records. Yeah, so instead of running things, yeah, I think that should work.
Okay, there are no other questions. We can thank Dima for an excellent talk, and
congratulations for the awards again.
Congratulations for the award.
Thank you.
Okay, so class dismissed, and tomorrow we have a morning session for those who live in the right parts of the world. So everyone is encouraged to come.
I will apologize to the speaker for having abused my knowledge of the technology to ask a pointed question. This is of course, it's an ongoing issue for the cryptographic community. I think yeah, there's plenty of research for you to do in the future. And thank you for a good talk.
Thank you.
Okay.
And we're out of here.
Thanks, everyone. See you tomorrow.